Thank you. Yeah, it's a real pleasure to be giving this talk today, and my apologies for not being able to join you in person. It looks like it's a really fantastic workshop. So what I want to do today is just give you a taste of what have been some of the recent developments and what I think are some of the really exciting prospects we have on the future for astrophysical searches for dark matter. And I think one of the defining characteristics of this field is the sheer volume of probes that we have available to us to try and elucidate the particle nature of dark matter. So I'm showing you a subset of the probes on the slide here, but for a much more complete discussion of this, I refer you to the white paper we're putting together on the topic that's being done in collaboration with the authors at the bottom of the slide there. So the hope is that with the data we've already collected, but more importantly with the data that we're going to be collecting in the coming years, we can finally start to answer some of these fundamental questions that we have in the field of dark matter. Like, could dark matter still be a WIMP? It's just a candidate that we haven't been able to probe yet. Or alternatively, does dark matter behave more like a wave, as we heard from Marsha in the last talk? Alternatively, it could be the possibility that dark matter exists in some broader dark sector. And actually, the first particle hints we will get is one of these dark sector states appearing in one of these modifications rather than dark matter itself. I think there's reasons to be optimistic that we could probe these questions in the coming years. So as many of the speakers have said, the fields that we've been asked to cover are very vast. So let me just give you a very biased a summary of one of these directions. Now, something I'm particularly excited about, and that's indirect detection. And I'll zoom in on this field even further and just look at indirect detection in X-rays and gamma rays, because I think there's a lot of exciting results coming on the horizon here. But just to mention a disclaimer, unfortunately, this means I'm going to miss out on what I think have been some really exciting developments in recent years. So for instance, the IceCube collaboration has really pioneered the possibility of looking for extremely high energy neutrinos coming from out in the universe. And there's still a large open question about exactly where are these neutrinos coming from, and the possibility that some fraction of that flux is coming from dark matter actually remains. Furthermore, there's been a number of interesting results released by the AMSO2 collaboration. For instance, we're now finally seeing a cutoff in the positron spectrum that many of us have studied. And furthermore, there's these tantalizing hints that they may actually be seeing some anti-helium events, even a few anti-helium-4 events. But I think on that front, we're really waiting to see what comes next there. Furthermore, there's actually been a realization in recent years that you can search for axions in these type of indirect detection searches. And one of the ideas is you can use radio to search for, say, axions. And this is actually something that Marsha touched on in the previous talk. So before I tell you about where there's work for theorists to do and what is exciting on the horizon, let me just get everyone on the same page to tell you sort of what are the fundamental ingredients when we're thinking about indirect detection. So this is the idea that dark matter may not be absolutely stable. Potentially it could decay, or alternatively, maybe dark matter annihilates. Either way, it could give rise to photons in the X-ray or gamma ray band that we can then go and search for. So to make this rough idea much more quantitative, we use the expression that I'm showing you on the slide here, which tells you what is the flux phi if dark matter is decaying that you would see at your instrument. So this is just a measure of how many photons would you get per detector area, per observation time, and then per region of the sky you're looking at. So of course it involves basic properties of the dark matter, like its mass or its lifetime, but there are also these other ingredients that I'll briefly mention in a moment. And also just to let you know, the equivalent expression if you're thinking about annihilation, I'm showing you on the bottom right. So let me tell you what are these ingredients on the right-hand side of this expression, because this is really where theorists can have input to optimize our ability to search for dark matter through indirect detection. So firstly, of course, how much flux I see at my detector from dark matter decaying depends on how much dark matter is out in the universe. And in recent years, and what's only going to accelerate in the future, we have a deeper understanding of how the dark matter in our universe is distributed. And we can use this insight to inform where should we be looking on the sky to see these decaying dark matter signals. This, of course, will just optimize where the signal on the sky is, and then what you need to do is carefully think about what the backgrounds are, and then come up with some optimized analysis to search for these processes. Another place where theorists can make improvements is in this indirect detection spectrum, this DNDE I'm showing you here. So what this controls is, let's say the dark matter decays, and then I'm looking for the decay products in neutrinos. I want to know what is the energy distributions of the states coming out here, but I could repeat the process for photons or potentially even anti-helium. Fundamentally, what we're doing here is just bread and butter field theory. We calculate differential decay rates or differential cross sections in the case of annihilation. And in certain cases that I'll mention, there's actually a lot of work to be done in calculating these spectra so that we can analyze experimental data with confidence that we actually know what we're looking for. The idea then is that we combine all of these quantities into this flux, and then we turn to the experimentalists to see what data they're collecting. And for example, this is where something that's so exciting about the field is that there's really fantastic data sets provided by, for instance, the Hess telescope I'm showing you here, which can see up to TeV energies. So I've already given you a taste about where theorists can contribute to this, but now let me just tell you what the experimental landscape looks like. And the reason I want to do this is, at least for me, it motivates where there is clear theory work to do in the next 8 to 10 years. So what I'm going to be doing is comparing different experiments on this landscape I'm showing you here. Let me quickly break down what the axes are. On the x-axis, I'm showing you the photon energy, because again, I'm just focusing on this specific form of indirect detection, going all the way from 0.1 keV up to about 2 PeV. And I'm also showing you a specific energy range of some of the data sets we have available, like E-Rosita down at the X-ray. That's an image of the X-ray sky. And then in the intermediate region, we have, say, a Fermi image of the sky as well. What I'm showing you on the y-axis is just one way of comparing different indirect detection instruments. In particular, I'm choosing to show for you the effective area of the instrument multiplied by how long it's made observation, so the observation time. The reason I'm showing this quantity is that, after some caveats, if you multiply this by the dark matter flux, it roughly tells you how many photons you should expect to detect. And of course, you need that to be a number of 1 or greater if you really want to make a discovery. Of course, this is just one way of comparing different instruments. You can actually roughly think about this as sort of the analogy or analog of integrated luminosity for colliders. Of course, how well we reconstruct the photons that come in can also be a very important quantity, but that's something I'm completely brushing aside here, but I just want to mention that. So having mentioned the disclaimer, now let me tell you where we're at the moment in terms of the experimental landscape. And you can see we have wide coverage over these many orders of magnitude in photon energy. So there's this Hess instrument that's sensitive up around the TeV energies I showed you earlier. Then we have coverage all the way down to very good instruments in the X-rays, like the European Space Agency's XMM Newton shown here. But that's where we're at. Of course, the whole process of Snowmass is about looking forward. So let me tell you where we hope to be in the next decade. And this, you can see that there are particularly dramatic improvements that are going to be expected at the highest energies. And actually, while I list LASSO here as a future instrument, this is this instrument at the very right of the plot, actually, as they've been constructing the array, they've been collecting data. And already last year, they announced the discovery of a 1.4 PeV photon, which is actually the highest energy photon we've ever detected as a species. So again, the point of this is to motivate where there's theory work to do. So now, having told you where we hope to be in the coming years, let me say what I think that motivates for where exactly we should be putting our efforts as theorists. And to begin with, I'll focus on what I think is where we're going to have the most dramatic improvement. And that is what jumps out from this plot is the highest energies. So this is going to be a combination of this LASSO instrument, which will be coming online very soon. There's the Cherenkov telescope array that was actually going to begin construction in 2020, but unfortunately, due to the pandemic, that's been delayed. So hopefully that will catch up to speed soon. And then also there's the Southern Widefield Gamma Ray Observatory that hopefully will be operating by the end of the decade. So in 10 years, all of these instruments should be collecting data. So let me tell you, what I think this provides for us as theorists is a mandate to make sure that these instruments have accurate theoretical calculations when they're going to search for dark matter in their data sets. And let me just give you one example of what the stakes are when we're thinking about this data. For example, in a study I was involved in that came out last year, we showed that the CTA instrument should actually be able to probe the thermal Higgsino at its predicted relic cross-section. So just to zoom in, what I'm showing you in this plot here is the expected reach at 5 sigma for discovery of CTA. This is this red dotted line here. And then what I'm showing you in gray is the leading order prediction, but including Sommerfeld enhancement. And critically, this red dotted line gets below the gray band. So this, of course, this Higgsino candidate is one of the well-motivated WIMP dark matter examples, and actually one that Raman touched on Wednesday. And so while it's been very hard to probe so far, CTA may well be able to touch this. However, something that's been realized in the last 5 to 10 years is that actually this leading order calculation I'm showing you here can be quite inaccurate. At least there could be some order 1 correction that needs to be added into this. And this is coming from higher order effects associated particularly with electroweak corrections, because this dark matter candidate carries SU2 charge. And so, for example, there's been a huge amount of effort in calculating exactly what do these effects do in the case of the theoretically simpler Wino. And there I think we have the calculation under control, but there's several reasons why the Higgsino is somewhat harder. And so extending these calculations to the Higgsino will be critical if we really want to determine whether or not CTA will see this candidate. But that's just one specific example. I think with this experimental program, we could actually hope to probe heavy dark matter much more generally. And there it turns out that the tools we have available at the moment are somewhat lacking. To give you an example of this, if we look at extremely heavy dark matter, I'm showing you a dark matter mass of an EeV, so about 10 to the 9 GeV, you can see that what experimentalists were using at the time was they're actually able to run Pythia at EeV energies. Now, Pythia was, of course, a software designed for much lower center of mass energy, so this might seem somewhat ridiculous that they were doing this, but there was nothing else available in the literature at the time to actually calculate spectra at these very high center of mass energies. So some early steps to improve upon these results show that the missing effects in certain channels can be dramatic. You can see the improvements of the spectrum here can be orders of magnitude different. And so I think more broadly, it's going to be important to make sure that we at least get orders of magnitude level spectra right, and hopefully do even better. And just to mention that actually a lot of the theoretical ideas that will be required to get this level of accuracy also come up when we're thinking about trying to get accurate results for 100 TeV collider. Because again, it's a lot of these electroweak effects that are important that also become relevant there. So that's all I want to say about the heavy end. Let me tell you what's happening down at these lower energy scales that you can see. So I actually lied here a bit. You can see that there's some progress, but this progress will not be achieved in the next decade. Actually, Athena won't launch until the mid-2030s, and E-Astrogam and Amigo aren't actually fully approved yet. But my understanding is that even if they are approved, they probably won't fly till the 2030s either. So then what we're looking at here is that in many cases, of course, up to the caveats I've made about this plot earlier, we're really looking at the best data sets that we can expect right now. They're already on disk. And if we want to get further improvements in indirect detection at these energy ranges, as theorists, we need to come up with new ideas for how to exploit this data. So there's lots of ways that this is being pursued. In a moment, I'll just dive into one particular example. But before I do so, I just want to mention some fundamental aspect of this plot here. And that is that it's actually fundamentally very difficult to go much higher at these lowest energies. And this is because for these low energy photons, we can only observe them from space. We can't see them on the surface of the Earth. And famously, getting a satellite into space and having it launch is very challenging. I'm sure as anyone who's been following the JWST launch would be aware of. So about the best we can hope to do is, say, a meter-squared instrument, getting that into space and operating it for about 10 years. And if you achieve that, then this is roughly how sensitive you should be. And you can see that's already what Fermi is hitting. In the future, what Athena will hit. But going parametrically beyond that is fundamentally hard. So actually, the ideas that we develop at these lowest energy scales will be useful more generally, not just in the next 10 years. I think it's going to be very hard to do much better than this, even in the far future.
So Nick, you have 2 minutes left. 2 minutes.
Thank you. Great. So let me just focus on one particular example of where I think there's work still to be done at this lower energy case. And this was an instance that Tim Tate touched on briefly in his talk on Wednesday. And this is this long-standing anomaly of the galactic center axis. So I'm sure many of you have followed this. This is an anomaly seen in the Fermi gamma ray data of dark matter annihilation, potentially peaking at about 2 to 3 GeV. But exactly studying what this is has been something that has dominated the field for at least a decade now. And actually, the field had really thought this problem was somewhat resolved around 2016. In pioneering work of Lee et al. And Bartels and collaborators, they show that actually, while this signal has some evidence that it looks like dark matter, it's much more consistent with a population of unresolved point sources like millisecond pulsars. And I think largely that was the accepted fact in the field for a long time. However, more recently, the situation has been changed dramatically due to work by Rebecca Lean and Tracy Slatcher. And particularly in 2 papers that they had in 2020, they showed that you need to interpret these results very carefully, especially the statistical results of Lee et al. And they showed that there can be systematic biases that can fool you into thinking there's a population of point sources in your data when in fact there are none. So this has really reinvigorated the possibility that there could be some dark matter anomaly in the GCE. I mean, I don't think that's the most likely possibility, but what I do think is the case that we really need to revisit these methods and try and understand, can we come up with much more robust analysis strategies to get beyond the lessons that Lean and Slatcher have taught us. And so this has become a small cottage industry. There's a lot of effort in the community trying to come up with these types of techniques. Without going into any particular details, I just want to draw your attention to one specific aspect of this plot on the bottom right. This is just some way of detecting point sources. And if you have a conventional technique, you have sensitivity at this gray band here. The hope is with these more refined techniques, you can actually almost push down to this orange dotted line I'm showing you here, which is orders of magnitude beyond what conventional techniques can do. So this is just giving you some flavor about how with these ideas, we might actually be able to get a lot more out of the data we already have. And so I think this is a very fruitful direction to pursue. So let me just wrap up there and sort of summarize by saying, I think experimentally, there's some very exciting results that are going to come out in indirect detection in the coming years, especially at the highest energies. But if we're really going to, for example, be confident that we're seeing some signal of xeno dark matter, there's a lot of theoretical work that needs to go into making these predictions that we have for that robust. And then to step back further again, I was just zooming in on one of the potential probes we have of dark matter using astrophysical observations. When you take the sum total of all the different observations that we have coming online, I think there's every reason to be optimistic that the next decade may finally start to give us some hint about exactly what the particle nature of dark matter is. Okay, I'll leave it there. Thanks for your attention.
All right, thanks for this really nice talk. Are there questions in the room or comments? Anybody going once? Yes, Yudan.
So yeah, thanks for the very great talk. So these are very exciting. I want to ask, is there any like indirect detection that is focusing on that, like dark matter just with gravity, like to your knowledge?
So do you mean
or like indirect effect, for example? Yeah, thanks.
Yes, so in terms of the probes I mentioned at the start, there absolutely are some that can look at just purely gravitational effects of dark matter. So for example, I mean, one of the basic properties is how does dark matter structure? And so for instance, something I touched on earlier on, or one of the examples I showed, is we're getting much more precise measurements about how substructure is distributed in the Milky Way, for instance. And so this could give us some hint into the properties of dark matter just through gravitational interactions without even looking for it directly interacting with the standard model, for instance. But that's it's a really interesting direction, and we're going to have a lot more discussion of that in the white paper. So please take a look.
Other questions or comments? Yeah, Nathaniel. Yeah.
Great. Thanks, Nick. This is Nathaniel Craig. You mentioned briefly, give a nice example of application of machine learning techniques. Do you want to say something more broadly about where you think the opportunities are for machine learning in this direction in general?
Thanks for the question, Nathaniel. Yeah, that's the thing I would say about this field is I actually think that machine learning has not been applied to this this area very much so far. And one of the fundamental challenges is that, I mean, we're not really sure we can always make training data because there can be, fundamental aspects of our background model that can be enormous and we have no idea about. I mean, the galactic center excess could be one of these. But I think what we've appreciated, I mean, really, for myself, after diving into these issues that were raised by Rebecca Lean and Tracy Slatcher, was that actually these likelihood-based approaches that we have, while we can make improvements on them and make them more robust, actually to feasibly compute them, you can show that you have to make fundamental approximations to what the true likelihood is. So essentially, I can't evaluate the true likelihood. I know what it is, but I can't evaluate it. And so then thinking back to the talk we had from Jesse, I think this is an area where really, at least the exact computation of the likelihood is something that I can get a machine learning algorithm to do. And so this is the direction where, rather than just trying to tackle all of the many challenges of the background model, here's a really well-defined problem. There's a likelihood I can't compute exactly that I can set a machine learning algorithm to. And this is the direction that, at least in the short term, I see a lot of application for. And that's what I've been thinking about.
Fantastic. Thank you.
No, thanks for the question.
Yeah, I don't see any more hands, so we should thank Nick again.